Good morning, listener. My name is Kenzo Liu.
Hi, I'm Jennings Ngo.
And I'm CJ Regala.
And we are Group 9. So today, we are going to be talking about glass and ceramics.
Here we have those two, glasses and ceramics, which are similar but also different. Glass is an organic solid material that is often transparent or translucent and also hard, brittle, and impervious, or in other words, impermeable to the natural elements. Glass has been made into practical and ornamental objects since ancient times, and it's still very important in various applications such as building construction, housewares, and telecommunications. Glass is made by cooling with sufficient rapidity the molten ingredients such as silica sand to prevent the formation of visible crystals. On the other hand, ceramics can be defined as heat-resistant, non-metallic, inorganic solids that are generally made up of compounds formed from metallic and non-metallic elements. Although different types of ceramics can have very different properties, in general, ceramics are corrosion resistant and hard, but then brittle. Most ceramics are also good insulators and can withstand high temperatures. As I've mentioned a while ago, glass and ceramics, though in some ways are similar, are still a bit different. Glass, for example, contains impurities that prevent crystallization. This is because glass is an inorganic product of fusion that is cooled to a rigid condition without crystallization, as opposed to ceramics, which are inorganic, non-metallic, crystalline solids. Moreover, glasses are amorphous solids, which means that they have no real or apparent crystalline form. Another characteristic of glass is that it tends to soften over a range of temperatures before becoming liquid, while ceramics have high and well-defined melting points. Another difference is that glasses tend to be translucent, while most ceramics are opaque to visible light. With the two having quite similar properties, some changes could create a new product, an example of which is glass ceramics. Glass ceramics is a product formed by the controlled crystallization of a glass-forming melt. It is a structure that contains of many tiny crystalline regions within a non-crystalline matrix. This structure gives some properties of ceramics and some of glasses. Glass ceramics also expands less when heated than most glasses, making them useful in windows, for wood stoves, or even as radiant glass ceramic cooktop surfaces. Now that we were able to define glass and ceramics, and we were also able to identify the existence of a product that is basically a combination of the properties of the two, we can now focus on ceramics. There are two main categories of ceramics: traditional and advanced. Traditional ceramics include objects made of clay and cements that have been hardened by heating at high temperatures. Traditional ceramics are used in dishes, flower pots, wall tiles, etc. The other category is advanced ceramics. Advanced ceramics include carbides such as silicon carbide, oxides such as aluminum oxide, nitrides such as silicon nitride, and many other materials, including the mixed oxide ceramics that can act as superconductors. Advanced ceramics require modern processing techniques, and the development of these techniques has led to different advances in medicine and engineering.
So let's talk about the different types of glass and ceramics. So for glass, we have fused silica glass. So fused silica glass is when silicon tetrachloride undergoes pyrolysis, which is also known as the decomposition due to high temperature. So other characteristics of it is that it has low expansion and high softening point, it has high thermal resistance, and it is transparent to ultraviolet radiation. Because of these characteristics, it has several applications such as optics and lenses for ultraviolet spectrum, starting material for optical fiber, windows for spacecraft, halogen lamps, and for semiconductors. So next, we have soda lime glass. So this is the most common type of glass since 95% of all glass manufactured is soda lime. So the typical composition is 70 to 74% silicon dioxide, 8 to 13% lime, and 13 to 18% sodium oxide. So it melts at relatively low temperatures, and it is also chemically resistant. So it is easily resoftened. So its applications, it is used in bulbs, window panes, bottles, Tupperware, and containers. So next we have lead glass. So for lead glass, lead oxide is used instead of calcium oxide. So it has high index of refraction and dispersion, and it is also electrically resistant. So it's often used in electric light bulbs and protection against nuclear radiation. Next we have borosilicate glass. So typically it contains 10 to 20% boron trioxide, 80 to 87% silica, and less than 10% sodium oxide. So it is known for its low expansion coefficient, resistant to shock, and chemical stability. It is also known as Pyrex, and it's mostly used in laboratory. It is also used in high tension insulators, pipelines, and telescope lenses. So lastly, we have alkali silicates. So it has two components only, sand and soda ash. It is also known as water-soluble glass or liquid glass. So its applications, it is adhesives for papers, detergents and soap building, fireproofing, textile, and silica gel production.
Okay, so now let's discuss the history of glass and ceramics. So first, around 28,000 BCE or before the Common Era, ceramic figurines are used for ceremonial purposes. 7,000 BCE, sharp tools made from natural glass appear. 5,000 BCE, Phoenician merchants possibly make the first glass. In 3000 BCE, glazed pottery is produced in Mesopotamia. In 1500 BCE, Egyptians start building factories for production of glassware. In the 1400s, high-temperature furnaces are developed in Europe for metallurgical use. In 1843, Henry Bessemer introduced an early form of float glass. In 1959, float glass was invented in the United Kingdom by Sir Achister Pilkington, and in the 1980s, ceramic high-temperature superconductors are developed.
Next thing we're going to discuss is the market demand of glass. In this slide, we have the important points regarding the current status of glass substrate market. The glass substrate market is estimated to be worth $1.49 billion in 2017, and it is projected to reach $1.97 billion by 2022 at a compound annual growth rate of 5.7% between 2017 and 2022. The increasing use of LCDs in consumer durables, smart handheld devices, and automotive applications is one of the most significant factors projected to drive the growth of the glass substrate market. In addition, the growth of the semiconductor and electronics industries is further projected to drive the increased demand for glass substrates. Based on type, the glass substrate market has been segmented into borosilicate-based glass substrates, silicon-based glass substrates, ceramic-based glass substrates, fused silica or quartz-based glass substrates, and others. Borosilicate-based glass substrates type is the most widely used type of glass substrates owing to their superior properties such as low coefficient of thermal expansion, high chemical resistivity, and high surface strength. Moreover, if you look at the region market demand, Asia Pacific is estimated to be the largest market for glass substrates. The glass substrate market in the Asia Pacific region is projected to grow at the highest compound annual growth rate during the forecast period, owing to the presence of numerous electronics manufacturers in this region. China is expected to account for the largest share of the glass substrate market in the Asia-Pacific region in 2022. Along glass substrate market, we also have the flat glass market. The flat glass market is projected to grow from $92.90 billion in 2016 to $142 billion by 2022. The growth of the market can be attributed to the high demand from the construction and infrastructure industry and emerging application industries such as automotive and transportation, and even solar energy. The market witnessed a significant growth in the past few years due to the increased demand for flat glass from China, the US, Germany, India, Brazil, and Malaysia. Asia Pacific was the largest consumer of flat glass in 2016. Moreover, India and China are major markets for flat glass due to growing construction and infrastructure development activities, increasing automotive production, and rising installations of solar panels in both countries.
Okay, so now let's get into the process description of the Pilkington process or the float glass process. This process was invented by Sir Alastair Pilkington in 1952. This process is used to manufacture clear, tinted, and coated glass for buildings and vehicles. So first, let's discuss the raw materials needed for the Pilkington process. So first is silica, or sand, and this is responsible for forming the glass. So this is sourced from sand dunes quarrying sites, and silica should almost be pure quartz and less than 1% iron, since iron can affect the color of the glass. Next is soda ash. Soda ash is used for oxidizing the iron, and it accelerates the melting of raw materials in the heat furnace. Soda ash is sourced from mineral deposits. Limestone is used as a stabilizer and is sourced from mineral deposits. Meanwhile, cullet or crushed glass saves energy during glass production, and it is sourced from internal and external recycling operations. Alumina lowers melting point and provides increased durability of the glass, and this is sourced from mineral deposits as well. Boron oxide is used for its high fluxing power as well as increasing the durability of the glass. It also lowers the expansion coefficient of the glass, which is related to thermal expansion. And thermal expansion is the tendency of the matter to change its shape, area, and volume in response to a change in temperature. And finally, salt cake is a fining agent that removes scum from furnaces. So both boron oxide and salt cake are sourced from mineral deposits. However, salt cake can also be from byproducts of other processes in the chemical industry.
Now let's take a look at our block flow diagram for a typical glass making process. So first, the raw materials enter the mixer and are joined together. After this, they are directly transferred into the furnace. During this part, as much as possible, we want to lessen the contaminants, such as dust particles and air holes. So once it is now in the furnace, fuel is used and it is heated at around 1600 degrees Celsius. After that, it is transferred onto a tin bath. So a tin bath is when the molten glass is allowed to flow on top of molten tin. These two substances do not mix, and since molten glass is less dense than tin, it floats. And this allows it to be perfectly flat. So H2 and N2 is entered in the tin bath to prevent the tin from oxidizing. So the flat glass is now transferred onto an annealing layer. So annealing is basically just controlled cooling in order to reduce residual stress in the glass product. So after that, it usually undergoes cutting. So during cutting, the excess glass or waste glass is transferred onto a grinder or miller, which turns it into cullet. Cullet is an important raw material for glass, so it is basically a recycled stream that will mix with the fresh feed that enters the mixer. After that, the final product is now ready. There is an 87% conversion from raw materials to glass. Here is our process flow diagram. For a more detailed discussion, please refer to this video.
We produce around 9 miles of glass at our Yorkshire factory every day. It all starts as sand, soda ash, limestone, dolomite, calamite, salt cake and recycled glass that's melted in a furnace at 1550 degrees Celsius. From the furnace, molten glass flows onto the surface of a bath of molten tin. Next, the glass enters an annealing layer where it's slowly cooled to release any internal stresses. A state-of-the-art laser detection system then checks every square centimetre for the slightest imperfections before the glass is cut. The glass is then ready to be sent to customers or to be coated or laminated.
Here are the unit processes involved in glass production. First is furnace melting. In this unit process, the raw materials are fed into the melting furnace and are exposed to around 1500 degrees Celsius of heat for about 50 hours. The liquid molten glass is produced given the following reactions. The overall reaction on simultaneous fusion may be represented by the fifth chemical reaction shown in this slide. The second unit process is furnace refining. In the refinement furnace, the liquid gas is homogenized and purified by removing bubbles. Additionally, temperature is controlled in order to cool down the molten gas until its viscosity is suitable for the float bath.
So for the unit operations, we first have hopper. So the hopper is where the raw materials, namely sand, soda ash, limestone, and alumina, are placed into a hopper in proportions. The hopper is directly fed into the furnace in order to avoid contamination with dust particles. Next, the float bath. The float bath is where the liquid glass produced from the furnace is transferred onto. The temperature of this molten glass is about 1100 degrees Celsius, and it is allowed to float on top of a perfectly flat layer of melted tin. The molten glass is less dense than tin, which allows it to float. Tin and molten glass do not mix, and tin also has a higher boiling point than that of molten glass. The molten glass leaves the tin bath at around 600 degrees Celsius. And in order to prevent the tin from oxidizing, a controlled atmosphere of hydrogen and nitrogen is present inside the bath. The next unit operation is annealing. So annealing is the process of controlled cooling in order to prevent residual stress in the glass or prevent distortion. Rapid cooling of the melt is necessary to obtain a glass product rather than it be crystallized. This rapid cooling will generate internal stresses or constraints within the glass, which will be detrimental for the mechanical properties. These constraints can be relaxed by careful thermal treatment called annealing by lowering the temperature of the rigid glass ribbon that came out from the float bath from 600 degrees Celsius to 250 degrees Celsius by passing through a cooling tunnel called LUR. Good annealing is essential to produce good commercial glasses, as it assures durability. Non-annealed or poorly annealed glasses will be subject to low resistance to cracks or failures under small thermal or mechanical shocks. All along the cooling process, the viscosity of the glass increases from a low viscosity melt to a rigid material with a higher viscosity. A certain degree of freedom is necessary for the glass to relax the constraints caused by the rapid cooling, causing rearrangements in the glass structure. Good annealing can only be obtained in a relatively narrow range of temperatures. For a good annealing of the constraints, the viscosity of the glass should not be too high so that constraints may no longer be released, and not too low so that the glass will not retain its initial shape. The goal of the annealing process is to relieve the permanent constraints caused by the fast cooling below the strain point which occurred during the forming process of the glass, and also to give a final hardened form, making it less difficult to cut the glass and shape it accordingly. The next unit operation is cutting. The glass cutting process involves making a score in the glass surface with a diamond or special tungsten carbide cutting wheel, and then running or snapping the cut to break the glass at the score line. Diamond steels are used to trim and cut the cooled glass ribbon into sheets before being stacked into packs or cases ready for dispatch. The final unit operation of the Pilkington process is the grinding or milling. So recycled glass cullet is a low melting substance which requires less energy to melt than the virgin raw materials. In the recycling process, recycled glass cullet is fed for grinding into a ball mill in which it is ground to a very fine glass powder ranging from 100 and 500 microns.
So now let's talk about the factors affecting glass. So first, we have surface defects. So of course, the strength of the glass is directly influenced by surface defects. So during the blowing process in some glass, direct contact with cold form leads to formation of high surface defects due to abrupt solidification of a thin surface layer. Next, we have glass compositions. So this usually depends on the presence of glass-forming oxides such as beryllium oxide, calcium oxide, magnesium oxide, and etc. Next, we have technological factors. So under this, we have the speed of formation, geometry of products, performance of the glass furnace, temperature condition during forming, and the annealing conditions. 40% of construction glass is actually lost during shipping, storage, and installation. This is due not only to the mechanical damage to the surface, but also the corrosion processes that may occur, because glass often corrodes when exposed to moisture. And lastly, float glass surface sometimes has rough contact with the conveyor belt, which also damages the glass product. Next, we have homogeneity. So there have been previous attempts in making heterogeneous window glasses, which are 30% quartz. However, the components did not react with the other raw materials and the glass did not form. Instead, the other components just melted and the crystals formed. In addition to that, the product glass was also not strong. We also have annealing, which removes internal stress and influence of the environment. So, contamination of dust particles create microscopic craters that retain moisture, and also humidity leads to corrosion, as mentioned a while ago. So we also have temperature. So basically, it is important to make sure that the temperature of the furnace is in the correct setting of 1600 degrees Celsius in order to make sure that the raw materials are successfully converted into glass. Next, we have the static fatigue of the glass. So when glass is not properly annealed, as mentioned a while ago, the static fatigue tends to show in the glass product. Lastly, we have the influence of the size of the glass, which simply means that the thicker the glass, the more durable it is.
Now let's look at the conditions that exist within the Pilkington process. The raw materials first enter the furnace at 1500 degrees Celsius. Then it turns into molten glass and exits the furnace at 1100 degrees Celsius. The molten glass then enters the float bath at 1100 degrees Celsius, turns into a rigid glass ribbon, and exits at 600 degrees Celsius. This rigid glass ribbon then enters the annealing layer at 600 degrees Celsius, and it is cooled until it is 250 degrees Celsius. Then it is finally ready for cutting.
For the industry situation in the Philippine setting, we presently have Pioneer Float Glass Manufacturing Incorporated and San Miguel Yamamura Packaging Corporation. However, as seen in this slide, we presented three to include AGC Flat Glass Philippines Incorporated, which was the former name of Pioneer. Pioneer Float Glass Manufacturing Incorporated, or PFGMI, is the leading flat glass manufacturer in the Philippines. It was established in 1958 under the former name of Republic Glass Corporation and eventually became a wholly owned subsidiary of AGC in 2001, adopting the company name AGC Flat Glass Philippines Incorporated. However, in 2017, TQNP Glass Manufacturing Corporation acquired 100% of the AGPH shares, thus becoming the torchbearer for the flat glass industry in the Philippines, hence the new name Pioneer. San Miguel Yamamura Packaging Corporation, on the other hand, is a division of San Miguel Corporation. It is the Philippines' largest packaging company. It is known to be the market leader for glass bottles, crowns, roll-on pilfer proof caps, two-piece aluminum cans, and plastic crates and pallets. It is a joint venture of two solid names in the field of packaging, San Miguel Packaging Specialists of the Philippines and Nihon Yamamura Glass Company of Japan.
That's all for today, folks. Thank you so much for listening, and we hope that you learned a lot. Here are the sources that we used for this presentation.